Once again, welcome to Physics STPM. I'm your instructor, Mr. Koo. Today's topic is 3.2, Principle of Conservation of Linear Momentum. Right? I prefer to use short form, P, O, C, O, L, M, rather than always anytime written there. Right? Previous short form that I have used to be Newton's first law of motion, NF-LOM. Newton's second law of motion, NS-LOM. Newton's third law of motion, NT-LOM. Right? Let's summarize for you what we are going to study. Right? That is the principle. Total momentum of a system of interacting bodies remain constant provided no external force acts on the interacting bodies. Okay, do your own mind map. This is my own mind map. Right? Newton's first law, second law, third law, important to memorize. Then we have defined momentum, right? Vector quantity. And then from Newton's second law, tell us how to calculate the resultant force. Right? This one, or that one there. And from there, we get this formula. And from there, we get calculate weight. Okay, so just summarize for you. Change the momentum that we have studied, force, or if momentum, the mass can change, velocity can change, then we differentiate. Linear momentum is conservation, that's what we will cover. And elastic and inelastic collision. 3.4, center of mass, which is another lecture. And frictional force. Right? Today we'll try to cover these two topics, 3.2 and 3.3. Look at the syllabus, 3.2, linear momentum and its conservation. State the principle of conservation of momentum and verify the principle using Newton's law of motion. Apply the principle of conservation of momentum. Define impulse, we have defined it in our first lecture. And then solve problem. Okay, state means you have to memorize it. Principle of linear momentum. If objects collide, the total momentum before collision is the same as the total momentum after collision, provided no external force. For example, friction act on the system. Right? Or just to summarize it, sum of momentum initially, sum of momentum finally. Right? Linear means it's on a straight line, one dimension. Provide for linear momentum to work, for the principle to work, there must be a condition. No external forces, no friction, no external force, or sometimes we call it closed system. You can get a note for A level here on this website. Usually, we instead of applying to collision, we call it interacting bodies. Interacting bodies can be explosion, can be radioactive decay, can be collision also. Right? Explosion or radioactive decay. Right? So total momentum of a system of interacting bodies remain constant, provided there is no external force act on the system. So different way of writing the same thing. Total momentum is always constant, whether before or after, remains constant, provide no external force and it. Right? Key is no external force or closed system. Linear means a straight line motion, provided the condition is met. Right? Mathematically, momentum is constant, resultant force is zero, or total momentum initially equals total momentum finally, or right, you can take that across there. Sum of final minus sum of initial will be zero, no change in momentum. Collision. Collision is an incident that happens in a short time interval of time. Motion of bodies before is different from the motion after collision. You can see that the velocity is different. The system is considered a closed system. No external force are involved. Is this a collision? If we have a frictionless ground, this is a trolley A, trolley B, different mass. This is Cambridge A-level. Came out in 2010, June 21. There's a spring. Compress it together. Right? Trolley push to compress the spring. This is a simulation or explosion. Right? Question to ask is, short time interval, yeah? Compress it, let go, it will shoot off in two different directions. Motion before and after is different. Initially, it's not moving. Closed system, if there is no frictionless force, right? So it's a collision. So example of interacting body will be explosion, firing a gun, colliding cars, radioactive disintegration. Okay, so it can be many cases at head-on collision. Colliding bodies travel in a straight line before and after collision. That's the key. Before collision, after collision, they travel in a straight line. The bodies travel in the same, right? In the same or in opposite direction after collision. Right? Opposite direction after collision. We are not interested in this one. This is not head-on collision. This is two-dimension. Right? Previously, we studied just a review of our first lecture on Newton's law on momentum. Okay, momentum time graph has a change in momentum. Right? Same. This can be a velocity time graph. Then this will be final velocity. There will be initial velocity. Then the gradient will be acceleration. There's uniform velocity. Right? So this is uniform acceleration or a constant force acting on the body. Right? And then we define our force as change in momentum over the time. Right? So the force can be obtained from the gradient of the straight line. So if you are required to draw the force for this diagram, the force time graph, right? Constant force, then zero force. Okay. Or you can use calculus to help you. Right? STP, dt, calculus that is area under the force time graph. Okay, collision. Suppose sphere A, that's your sphere A, or mass MA, moving. This is usually initial speed. So this final, usually the final speed. Suppose sphere A, or mass MA, and moving with speed UA. Okay, that's your sphere A, mass MA, velocity UA, collide with a sphere of mass MB. There's a sphere of different mass MB. That's the initial velocity of UB. With velocity UB collide head-on, and after collision, the sphere move off with velocity VA. Okay, should be able to read. This is after collision. This velocity after collision. So A rebounds with VA, B rebounds with VB. Right? Remember, momentum is a vector, so we have to choose a direction as positive. Right? So usually we choose to the right as positive. Then you should be able to write the equation. Right? Conservation mass times UA as the initial momentum of sphere A, mass MB times UV. Right? Remember that negative sign there equals to your mass MA. Right? Is negative to the left times your VA and there is a mass of VB times your VB. You should be able to write out the equation. No matter what they give you should be able to write conservation of momentum. Okay, now we are going to show. Right? Previously, we write this conservation of momentum. Now we are going to derive this equation. Right? Let these two spheres collide. Right? Principle of conservation of linear momentum can be obtained from Newton's third law of motion and Newton's second law of motion. Okay, body A and body B colliding. Right? This A has the speed, has the initial speed and final speed. That's the initial and final speed of B. Okay, so B will collide with A with a force FB. Force of B on body A. Then you have FA. Force of body A on B. Right? Some people will prefer put an A there also lah. Then put a B there also lah. It doesn't matter lah. As long as you define it clearly. Since both are action and reaction force, you apply Newton's third law of motion. Right? FA is equal to FB, but there's a negative sign there. Right? Let's consider the time of collision is the same. Right? A hit B and B hit A. The time of collision is the same, T. Right? We're just going to use this equation to find this force. We look at this velocity. Okay, so this is MA into right, initial speed, positive direction. There's a final one. Final one is not more, not positive already. Negative direction. Put negative sign there. Same. Right? FA. Look at these two velocity. This MB. There's a mass MB. Final one, positive, correct. Initial one, negative. Right? Negative, negative becomes positive. Right? T is the time of collision, is the same. Right? We can cancel T or multiply by T to get rid of T. And take all the final to one side, initial to one side, to get our answer. Okay. This is the final. This is the initial. Take it across there, you got that. Positive. This is final. Take to the other side, becomes positive. This is negative. Right? That's why we get negative. Okay, that's what we write down just previously. Right? MA times UA minus your MB times UB. Right? And check and see. And MA minus MA times VA equals to MB times VB. Right? Should be able to draw the graph of momentum against time. Right? Before collision, you should be able to write down the before collision. Right? That's the momentum of A initially. That's the momentum of B initially. Okay, B is negative. B is positive. Then they collide. This is the time of collision. Remember, that is the force. And then final momentum. Right? After collision, it goes negative. Right? Goes negative. Collision, this goes positive. Right? The slope must be the same. Right? Remember, this is idealized. That means it's perfect. Perfect. We smooth it out. It's supposed to be a curve at this part there, curve at this part there, but we idealize it. Okay? Easier for us. Initial momentum is just your MA times UA. Right? For BI, PBI, mass times that. That's all. Right? You want to put a negative sign to show direction. So initially, these two add together. That's how we get Finally, these two are together. Right? It's negative, it's positive. Gradient gave the force on the body. Right? It must be the same magnitude. One is positive, one is negative. Okay, we've completed that. Now let's go to elastic and inelastic collision. What are we supposed to know? Distinguish between elastic collision and inelastic collision. Knowledge of coefficient of restitution is not required. Solve problem involving collision between particles in one dimension. Right? All collision can be classified either as elastic or inelastic collision. In all collision, total momentum is conserved. Total energy is conserved. Remember that. Total momentum is conserved. Total energy is conserved. In elastic collision, the final kinetic energy is always less than the initial kinetic energy, as some of the initial kinetic energy is converted to other forms. Right? Example sound when the two cars collide. Usually examiner don't like the term conserve. Right? When you write conserve, it doesn't tell anything. Maybe you don't know, you just memorize it. Right? So it's better to say sum of momentum before equals to sum of momentum after collision. In explosion or radioactive decay, the kinetic energy after the explosion is always greater than the initial kinetic energy, as chemical energy or nuclear energy provides the kinetic energy. Right? Initially, the explosive may have zero velocity. After that, they explode, they move in different direction. So they get energy. So the energy comes from chemical energy. No? Other example would be jumping a party, right? Plasticine. Collision between bodies, huge body like cars. In general, all about collision example between vehicle are inelastic. All that we see, all the collision that we see around us are inelastic. So part of the original kinetic energy is transformed into internal energy as work done in deforming the vehicle, sound, or other form. Right? You will hear sound when the cars collide, and then the damage, the deformed car, right? And that internal energy, which you study later on, is given out as heat, right? Thermal energy. In elastic collision, how do we recognize it straight away? Two bodies collide, and the two bodies stuck together. Example, in this case, after collision, they move off together. Or sometimes we use the term couple. After collision, then the collision is completely inelastic. Right? You can straight away say that it's inelastic. But usually examiner will prefer you to find the kinetic energy before and show the kinetic energy after. It's different. Elastic collision. In elastic collision, kinetic energy is conserved. That is the total kinetic energy before collision equals to total kinetic energy after collision. Here's the criteria. I for initial, F for final. We can summarize it. Right? Sum of kinetic energy initial, sum of kinetic energy finally. So you should be able to write. There's your mass MA times half MUA squared. Then if this one is moving the other way, I should be able to write mass MB UB squared half equals to, right? Doesn't matter. If you put a negative sign, your square becomes positive. Right? Final one, right? Square that becomes positive. MA half MA UA square half MB UB square UV square. I should be able to write out equation there. Example, atomic collision. Usually in the atomic realm, right? Big body collision like cars, person and person, dropping a ball. These are all inelastic. Collision between neutrons. Collision between billiard ball, almost, even though you may hear a little bit of sound. Recognize elastic collision and body A with an identical stationary body B. Right? Identical means they have the same mass. This is stationary. This is move with UA, U. Right? After collision, this one stop. This one move with the velocity U. Right? Basically, they interchange kinetic energy. Or other example, right? Exchange velocity. This is the case. A. This one is stationary, not moving. Move. Then the green one stop. Right? The kinetic energy is transferred to this one. Or they have same speed, moving in different direction. After that, they rebound off with the same velocity in different direction. Or this one move with greater speed, lesser speed, collide. After that, it gives kinetic energy to this one. The kinetic energy, because it gives to this one, the kinetic energy to reduce, becomes smaller. Right? So that speed is transferred to this one. This speed is transferred to that one. Right? That's how we can roughly see what's elastic collision. Okay, so do your own mind map. There are things that you need to remember, right? Summarize it, what you have studied. Right? In elastic collision, kinetic energy is conserved. Identical particles, exchange of velocity. Okay, so build up all the formulas that you need to remember. Okay, let's solve some problems. Right? Remember, you cannot study physics one. You have to, after understanding it, try the problem. Right? I'm using most of this book and this book. Right? Doesn't mean that you cannot use this book. This book got past paper, same as this book. But as first student I teach, he used this book, so I use this book also. Or some question from Cambridge A level, 9702 physics. Right? These are unofficial textbook. It's good enough. To use the reference book that's too thick and sometimes too wordy lah. A lot to study, a lot to read. Unless you got problem, don't agree with some of this unofficial textbook, then you go to reference book to check. Okay, let's try. This is an old Cambridge A-level question. Diagram shows two trolleys X and Y about to collide. Momentum of each trolley before impact is given. That's momentum before. Right? Remember, examiner will not give you a negative sign. They just give you the magnitude, give you the direction. After collision, the trolley travel in opposite direction. And the momentum of X equals to 2. What is the magnitude of momentum of Y? Right? Remember, momentum is a vector quantity. Choose the right. You can choose the left as positive or to the right as positive. Right? So it's your choice. I choose to the right as positive. This is positive. Right? That one is negative. I want to find that one after collision. This is negative. I have to put it myself. Right? Conservation of momentum. Sum of initially, sum of finally. Initially is this 2, 20 minus 12 minus 2 plus py. So py is 10. The answer is C. Okay, have a go at this one. Stop the video and have a go. Two similar spheres, similar means the same mass. Each of mass m and traveling with speed v are moving towards each other. The sphere have head-on elastic collision. Which statement is correct? The sum of momenta before impact is 2mv. Remember, right? Momenta is a vector quantity. So momenta mv for this one, the same thing, m minus mv, right? To the right is positive, this will be to the left negative. So subtract is 0, so it cannot be this one. Sum of momenta before impact, mv minus mv equals 0. Sum of kinetic energy before impact. Right? Kinetic energy doesn't depend on the negative sign there. It's half mv square. This is also half mv square. That's why we times 2 there. So it becomes mv square. Right? So it's not 0 because it's not a vector quantity. For elastic collision, sum of kinetic energy after impact. Yeah, that's correct. That's what we get. If it's elastic collision, it must be the same before and after. Stick together is usually in elastic collision already. Okay. Right. Let's just test you. See whether you can remember what we have just learned. Collision between objects are said to be either elastic or inelastic. Complete the table by placing a tick in the relevant boxes to indicate which quantity are conserved in their collision. Okay, elastic collision, momentum is conserved, kinetic energy is conserved, total energy is conserved. Inelastic collision, kinetic energy is not conserved as well. The other two are conserved. Okay, that's a ballistic pendulum. Okay, that's the ball. That's the catcher. Okay, pendulum initially at rest. You load the gun, right? Compress the spring, and then you fire the gun. The ball will hit the catcher, and the catcher will swing to a high there, and you can measure the angle from there. Okay? It's the ballistic pendulum. Measure the speed of the ball. Okay, have a go at this question. Ballistic pendulum is a device used to measure the speed of projectile, such as a bullet. A 5.4 gram is fired horizontally into a suspended 10 kilogram block of wood and causes the block with the embedded to move off with a 0.3 meter per second. What is the final momentum of the bullet? What's the impact velocity of the bullet? What's the maximum height of the block and bullet? Is the collision elastic or inelastic? Right? Always draw a picture. There's your bullet. There's the block of wood. Right? Initial state. We don't know the initial speed of the bullet. Let it be u. Mass you are given. That's your mass in gram. Mass of the block, 10 kilogram. After impact, right? The bullet embedded in the block. So now the two mass add together, you get this one. Right? Because they move together. And you are given the velocity here. Right? Remember this conservation of momentum, this part. After that, it has kinetic energy, so it's conservation of energy. Right? Kinetic energy converted to potential energy. What the high H. Right? To understand the problem, okay, find the final momentum of the bullet and block. Right? Just this mass times that, that's the final momentum. Okay, now the stages. First, it goes in. First, the bullet itself, and the bullet goes in, and you move with velocity v, and after that, it swings to a high h to an angle where the final kinetic energy or velocity is 0. Embedded means that the bullet remain in the block. Body move together. Final momentum of the bullet is the total mass. Mass of the block plus mass of bullet times the velocity of the block and bullet. Put in your value. That's your value. 0.3. Get that? Right. So we get. Then conservation of momentum. We want to find the initial speed. This one. Final momentum equals initial momentum. Right. That's the final one. Initial It's just mu. This is 0 because it's not moving. Right? Put your mass of bullet inside. This one convert it to kilogram. Using a calculator to calculate. And finally, part C. This one has a velocity. It moves to a high h. Right? Conservation of energy. This one gain potential energy. This one lost kinetic energy. The block and bullet move to a high h before returning. So that total mass g times h. That's the initial kinetic energy, half m plus m, v squared. M and m cancel off. G is 9.81. Divided by m and m. Or cancel m and m cancel off there. So this one is 9.81 times height, half v squared. V is this there. We've calculated out. Oh, given to us 0.3. Calculate our h using calculator. Okay. Okay. Is the correlation elastic or inelastic? Okay. The only way to find whether it's elastic or inelastic is to calculate the kinetic energy before collision and kinetic energy after collision. Right? Sum of kinetic energy initially is just the bullet, mass of bullet times the speed of the bullet, square that. Got that? Then after collision, that's the speed of the bullet and the block. We'll calculate the kinetic energy, half total mass. That's a total mass, velocity. They are different. Right? You can see there's a great loss in kinetic energy. So the initial kinetic energy is greater than final kinetic energy. So the collision is inelastic. Right? So we know moving together straight away is inelastic. But we cannot use that to say the answer is that. Right? That is the way. Show that whether it's elastic or inelastic collision. Right? Have a go at this one. Taken from your revision book, an official textbook. Two particles A and B, P and Q, of equal mass, traveling towards one another with speed u and v respectively, make an elastic collision. At some instant during collision, P is brought momentarily to rest. What's the speed of Q? Okay, either you picture in your head or you can draw on the exam paper, right? So they can see. Just a rough sketch. What is written? U and V moving together, so that is a velocity vector minus V. And then after the collision, there's your V. P is 0. P is brought momentarily to rest. So is a collision. We are going to use action and reaction forces, Newton's third law, and also Newton's second law. Okay, the time of collision is the same, so we don't have to worry, they cancel off. So we apply to this one, P. Right? Final one is 0. Final one is 0. Initial one is U. Mass is M. And this minus Q. Q is minus M. Right? That's your final. That's your initial. V minus V. M and N can cancel off. So we want to find V. Right? Take this one across there. This one the other side. Or another way, you can write this way. No answer. You can rewrite this way. Right? That means our direction is wrong. This direction will be the other way around. Okay. Suddenly this speed is greater than that speed. Sorry, this speed is greater than that speed. That's why it's going that way. Okay. A. Ago, a particle, stop the video. Particle of mass m traveling with a velocity u makes a head-on elastic collision with another particle of mass m, which is at rest. If m is less than capital M, show that the particle with mass m move in the direction opposite to the initial velocity after collision. Draw the picture. Draw a picture. Mass m, so velocity u, head-on collision with another mass m. Right? Draw it bigger, greater mass. This at rest. No need to draw the velocity. Show that the particle with mass m, right, smaller mass, move off in the direction opposite to the initial direction, initial velocity after collision. Right? Conservation of momentum, initial momentum, m times u. The one is not moving. And this one, v times m, capital M times w. Okay, we want mw. Take this one across there. Take the m, small m out, u minus v. Concentration of kinetic energy. Right? I told you elastic collision. So initial kinetic energy, this one is mass, half mu square. Final one is half mv square, half mw square. Okay, take the half and half cancel off. Take this one across there. Take the m out. Right. So that difference of 2 square, u square minus v square, right at that one there. Then we still got mw square. Okay. So we can take 2 divided by 1. That one can cancel off. mw, m cancel off. We still got w. Okay. So what can we say about here? Let's substitute in 1. We are more interested in v. Not interested in w. Right? So replace the w in 1. Right? mu, mv, replace that one with that one. U plus mu plus mv. Okay, we write that. We are interested in v. Take the v out. Take this one across there. So you got m minus capital M. And then this one is just m plus big M. Divide. So we can see that we are told already m is greater than m. So this is negative. Okay. That's how you show. Okay, let's try another one. Let's try the partial question. This one, partial question 2019. A particle P, right? A picture, particle P move with constant velocity and collide head-on with a particle Q, which is stationary. It's not moving. After collision, both particles move with the same velocity. Which statement is true about the collision? The increase in momentum of Q is equal to the decrease in momentum of P. Right? That's your momentum, M times U. The two move together, add the two mass together, that's your V. True. Increase in momentum of Q is equal to a decrease. Yeah, it must receive its momentum or kinetic energy from P. Right? If there's an increase, there must be a decrease in this one. The increase in kinetic energy of Q is equal to the decrease in kinetic energy of P. Yeah, let's look at that. Increase in kinetic energy of particle Q is equal to the decrease in kinetic energy of particle P. They don't tell you whether it's elastic collision. So in this case, if there's a decrease in kinetic energy, it will gain kinetic energy, but it doesn't not equal. It doesn't have to be equal. Total kinetic energy after collision of particle P and Q is greater than total kinetic energy before collision. Cannot be. Total kinetic energy after collision of particle is greater, cannot be greater, cannot be bigger, must always be smaller because it's lost as some other energy. The force acting by particle Q on particle P is less than the force acting by particle P on particle Q. It cannot be less. They are action and reaction force. The force should be equal and opposite. Newton's third law of motion. The answer is A. Okay. Have a go at this one. 2016. Sphere A and sphere B collide head-on elastically. Which statement is true of the collision? Right? As I always say, draw a picture. Then you can understand better. There is before collision, this after collision. The loss of momentum of A is equal to the loss of momentum of sphere B. False. When one sphere loses momentum, the other gain momentum. Right? Because it's collide. If this one going to lose kinetic energy, it must give kinetic energy to this one. So this one will change its momentum. After collision, the momentum of sphere A is equal to the momentum of sphere B. False. It's the total momentum. Total momentum of this before collision is the total momentum after collision. Right? It doesn't tell you about the direction, but it can just give a different direction. It doesn't tell you about the mass, it can give a different mass. The loss of kinetic energy by sphere A is equal to the gain in kinetic energy by sphere B. Right? They are towed elastically. So it means that if there's a loss of kinetic energy by A, it must gain by B. No, cannot turn to other form anymore. After collision, the kinetic energy of sphere A is equal to kinetic energy of sphere B. False. Total momentum is conserved. Total kinetic is conserved. That means the total kinetic energy of A and B before and total kinetic energy of A and B are the same. Not just A and B. That's all. Answer is C. Okay, let's try the structure question. Define impulse. Impulse is a product of force and duration of force acting. Using a suitable Newton's law of motion, derive an expression which relate impulse and velocity. Right? Impulse is force times time. So force, that's your force. Newton's second law. And then there's your time. Time and time cancel off. So equal to change in momentum. A piece of plasticine and a ball bearing of same mass are dropped vertically downwards from the same height onto a hard metal surface. Explain whether the plasticine or the ball bearing which would exert a larger average force on the surface. Since the height is short, air resistance is negligible. Both balls will reach the surface at the same time. the impact time if the surface is short for ball bearing, because ball bearing is hard. So the rate of change in momentum and thus the force on the ball is large. We are just using this formula. Right? Change in momentum. This is short, so the force is large. Right? It's larger than for the plasticine. Plasticine, the time is longer. Impact time is longer. Apply Newton's law. The force on the surface is equal but opposite. Right? Force on the surface is the force opposite to the force by the ball on the surface. A piece of plasticine. Now let's try to calculate number 2. Calculate the average force for the plasticine and the ball if the mass is 10 grams, 5 per meter, and the velocity of impact is, the time of impact, the duration of impact is 0.0 second. Right? Calculate the velocity before collision, right? Using conservation energy, where U is the velocity before impact. Right? As a potential energy, it has change to kinetic before collision. M and N cancel off, so it becomes your, take the 2 across there, put in your value, calculate out. And the force, right? We're not told the final, calculate the average force. If the mass is gram, duration, we are not told the final velocity, we just assume it's 0. And that is the initial one before collision. That's the time of impact. 10 gram convert to kilogram, calculate out. A bullet of 125 gram is fired horizontally with a velocity 315 meter per second into a block of wood of mass 1.5 kilogram, which is initially at rest on a smooth surface. Calculate the speed of the block after collision if the bullet is embedded in the block. Let the speed of the bullet and block be v. Right? It's the same as what we have done before. This one, except it's not a pendulum, it's lying on the smooth ground there. Right? Initially, this is at rest, embedded, they move together. Okay, so conservation of momentum. Mass of bullet, and inertial speed of bullet. Right? Remember to convert it to kilogram. Block is at rest, so no momentum for the block. And then the block and the bullet move together, so add the 2 mass together. Right? The total mass and final velocity, calculate out. Okay, thank you for your time. We hope to see you for another session later on. So we are end and finish for today. Thank you. Good night.